Okay, yeah, it's very, very nice to see so many people here and to have some familiar faces as well in the audience, as well as many new faces who I'm happy to meet. And maybe so many of you came because I put this very boastful title, Learning Physical Laws from Data. Is very catchy. Now I put a maybe a slightly more academic and humble title here, which is about statistical foundations of what people are calling scientific machine learning, and for PDEs. And so who knows what PDEs stands for here? Okay, who hasn't heard of PDEs? Okay, so actually quite a lot of you know. PDEs stands for partial differential equations, and I will briefly explain what they are. They describe a lot of physics, essentially. Actually, let me also ask, who here has a math background? Okay, how about computer science? Okay, and other. Okay, got it. Great. Yeah, it should be a fun time. So, just as a disclaimer, I am a mathematician. So there will be some technical parts, but I also have a lot of pictures. I did as well as I can, and I think like today we're gonna balance this together, and hopefully everybody will take something from it. So Duke already mentioned, so I'm not gonna say much about myself, but maybe just about my research interests. Essentially mathematical statistics, and this is a field that has grown a lot kind of recently with the advent of data science and AI, and so there's a lot of new mathematical questions that have arisen from lots of different algorithms and methods that have popped up. Similarly to maybe 100 years ago, or even starting even earlier in mathematical physics, that physics has provided mathematics with some of the really, really interesting mathematical problems. Okay, so non-parametric statistics is essentially the field of when you have very high-dimensional statistical models, right? Very large statistical models, and that often shows up in machine learning, I would say. Bayesian inference is something I work on, high-dimensional computation. So actually, how do you numerically evaluate complicated models, and generative modeling? So you can ask me about any of these. So I'm going to present work that that is joined with many co-authors, as well as, I'm only going to talk about that kind of in the second part of the talk, because I first want to give you a broad overview. Right? But these are some of my collaborators over the years, so I want to give them credit. Okay. So, as I said, PDEs stands for partial differential equations. And there's also a related type of equation that is called a stochastic differential equation. And together, they are used as models for actually a lot of what one can call, broadly speaking, a complex system, right? So some kind of phenomenon that occurs in nature or in society. And so they kind of describe how these systems evolve. Just to give you a few examples, there's this thing called inverse problems that I will introduce more formally later, right? Where essentially you're trying to reconstruct something out of indirect measurements. And a lot of inverse problems, interesting ones, come out of medical imaging, right? So let's say you have an MRI machine, and you can take MRI measurements, but you're not really interested in the MRI measurements themselves. You're interested in the brain image. And the thing that describes the mapping from the actual brain image to what you would get as an output in the machine is to a certain degree now not a differential equation, but some kind of operator that describes that, right? And a lot of other imaging modalities like X-rays are actually described by differential equations. Okay. Now, another very prominent example is, of course, weather and climate. So these are very huge differential equations, right? So these are very kind of local. You're modeling something that is the size of a soccer ball, and here you're actually solving things that are partial differential equations kind of on the global surface, right? And okay, another example would be molecular dynamics, where people are interested in actually, given some kind of sequence of atoms, how do they move in time? So this would be a stochastic differential equation that kind of it describes how this molecule jiggles around, and maybe it will assume one kind of spatial configuration and maybe hop to another one. And also, probably most of you have, since your attendance of this BLISS series, you know about generative AI. And generative AI, recently there have been a lot of generative models that are based on differential equations. So basically, you learn some kind of differential equation from data that transforms some kind of probability distribution that is boring and vanilla to a really interesting probability distribution, for instance, of cat images. And then you're able to kind of generate new cat images, right? And this works through learning a differential equation. Okay? So generally, as not just in the context of PDEs, but as a statistician, right? So this is your first takeaway. What is our goal, right? In statistics, we always have measurements, and they're typically noisy, right? So we can only make approximate measurements of our system. And we have models about how our data has been generated, right? So for instance, in weather, you would say, okay, I have some kind of very complicated fluid dynamical PDE, and I'm taking temperature measurements, right? And I know the temperature evolution in time and in space is described by this equation, right? And my goal might be to predict the weather tomorrow, or to calibrate some unknown things that are in my model, okay? So essentially, what is my goal? I kind of want to optimally combine some model for my data generating process and noisy measurements to do parameter estimation. That would be, for instance, calibrating this unknown thing in my model, right? A prediction, I want to extrapolate to the future or to other unknown, unseen scenarios. And often we also want to do uncertainty quantification. Okay, so I don't just want to say, well, tomorrow I think it's going to rain. But I want to say, well, I think tomorrow it's going to rain with 80% probability, which is what the weather report actually gives us, right? Okay, so these are big questions. That's the big picture. And of course, AI and machine learning has entered in a lot of these things now. So AI is being used to for instance, improve our models that we have, of these systems. I'm going to talk a bit about that at the end, right? But of course, AI and statistics are very close, right? So in a way, this is all under the umbrella of inference and learning in these kind of contexts of a complex system. Okay, so I'm going to now set the stage by telling you some kind of general framework that I'm going to operate in mathematically. And then I'm going to tell you a lot of examples of these data generating things. Okay. So just as a good motivation. So for instance, machine learning models have become really competitive in weather prediction, which is a huge achievement, right? So there's this thing called GraphCast that Google and DeepMind have been developing, and they get really fast and pretty accurate weather prediction. And essentially, they have, in a data-driven way, learned how to extrapolate from today's kind of state of the weather to, let's say, tomorrow's, right? And this is in a data-driven way, not by traditionally solving all their equation on a supercomputer. Okay, so we statisticians like this denoting whatever we're interested in by the letter theta. Okay, so let's say theta is some kind of unknown. You can think of it now as either theta is something I want to estimate, so I want to reconstruct, for instance, my brain image. Just think of theta as the brain image that I want to know, or you can think of something that I want to predict. Theta could also be tomorrow's weather, right? Okay, and in statistics we always have this thing that this unknown is contained in some kind of space of possible unknowns. So this is the capital theta set, right? Okay, and within capital theta, I want to know which one is the correct theta. Okay, and I'm going to talk about mostly today a paradigm that has been incredibly successful in this combining knowledge about the model and the data, which is the Bayesian paradigm, right? And the Bayesian paradigm has been really nice because essentially it is a probabilistic way of doing this kind of inference or prediction, right? So that automatically gives you uncertainty quantification, not just one answer, but actually you get a probability distribution of answers, and you can say, well, actually I'm 80% sure or 95% sure. Mathematically speaking, what does the Bayesian do? They're interested in this data, right? And they base all their statistical inferences on what is called the posterior distribution. So actually, in principle, Bayesian inference is super easy, right? It's just one formula that dictates everything, which is this formula, the Bayes formula, okay? So the posterior distribution is this thing, a pi of theta given Zn, right? And it's proportional, so this is a proportionality sign. It's proportional to the likelihood times the prior, okay? What is the prior? The prior is something that I need to choose that kind of says, okay, amongst all the thetas, I have some belief that some thetas are more plausible than others, perhaps, right? So I put a prior distribution of how likely I think that theta is going to be the right answer. But after observing the data, I'm going to update these prior distributions, right? Because maybe I thought some theta is really likely, but it actually doesn't match at all with my data. So I'm going to downweight that theta. And another theta, perhaps, that I didn't think was very likely, matches really well with the data, and I'm going to upweight that theta. And this is encapsulated in this likelihood function. Okay? So, so I have a prior distribution. I have this L, that is the log likelihood. So e to the L is the kind of plausibility of data, right? And so Z is my data. Zn is my data. Okay, and n is kind of a sample size. So yeah, we like to think about, as I get more and more data, what happens. Okay. Okay, so why is this difficult? Because this is actually very, who of you has taken a course, a university course in statistics before? Okay, and who of you hasn't? Okay, right. So you're familiar. Why is this difficult or modern, or why do we even need to think about these things? Well, because in these modern settings where you want to, maybe you want to apply this to a PDE system, the problem is that this dimension D of this set of unknowns is really huge, right? Because let's say you're modeling images that are 1,000 by 1,000, then this D would be 1,000,000. In reality, of course, it's probably there's some low dimensional structure, but D is really big, right? And also this likelihood function might be super complicated, right? So this, how well does my theta match with the data, right? That might involve some PDE, because you have to say how well does my theta match with this temperature measurements. Maybe you have to solve a PDE that corresponds to theta, right? Okay, so this is why it's hard. But once I do have this posterior, I can derive kind of different estimators or best guesses for my theta, right? So one thing I can do is I can say I pick this what's called the maximum a posteriori estimator, which is essentially I pick the theta that is most plausible according to this posterior distribution. So kind of in a combined way, what I believed before and after observing the data. So I literally I pick the maximizer of this posterior density, right? Another thing I can do is I take the average over all these over the plausibility. So this would be the posterior mean. And often they're a bit similar, as it turns out, okay? And the third thing that my posterior gives me is, as I mentioned, these uncertainty bars. And in Bayesian language, that would be called credible sets, okay? So here I have some curve that I would like to estimate, this blue dotted curve. And I have noisy measurements, which are the blue dots, the thick dots. And the orange stuff is my estimation based on the posterior distribution. And in machine learning, this is something people would call Gaussian process regression, right? So what they have done is they have put a prior on all possible curves, and the posterior on all possible curves, we can't fully draw it, but the mean is this orange line, right? But actually, okay, now we see here that in this area we have many more measurements than here. And accordingly, actually the credible sets the uncertainty bars are wider in this area where I have less measurements, right? And that's something desirable because, okay, without reporting these uncertainty bars, I wouldn't know that I might actually be much further off here. So I should trust my inference less, right? But so that's the good thing about uncertainty quantification. Okay, so as mathematicians, what do we think about? Just to give you a sense of, this mathematical statistics community, they care about certain types of questions. So, for instance, if I get more and more measurements, more and more blue dots, how fast do I approach the blue dotted line, right? Okay. And the second thing is, now I need to also compute these things, right? So in order to actually implement my Bayesian inference on a computer, I need what's called Markov chain Monte Carlo algorithms. I need to generate samples from the posterior, right? And actually with a lot of stuff, so you probably all know gradient descent, a lot of these algorithms, we don't actually know whether they have converged or not, right? So one thing I have been thinking about a lot is actually kind of these theoretical guarantees for these kind of algorithms. Okay. Okay. So I already mentioned. Okay. So what are challenges? You might have very kind of nonlinear dependencies of theta and the data that you observe. You have high-dimensional problems that are non-convex, right? And this is a problem for the optimization and sampling algorithms. So you might be sampling from a distribution that looks like this, that has multiple kind of plausible areas, and algorithms can easily get stuck in these kind of local maxima. They might think that they've already found the highest probability region. And the third thing I'm gonna talk about, hopefully, it's probably too, or might not get to it, are that these likelihood functions, when they're very complicated, they are very expensive to evaluate. And so people have been trying to learn AI surrogates using neural networks for that. Okay, and we're developing some statistical foundations for that. Okay, so one general setting that is relevant in this context, I already told you, are inverse problems, right? And inverse problems are actually very easy to formalize in general, mathematically. All you have is this kind of ominous map G, okay? And this ominous map G maps functions f to some other space y, where your observations live, right? Okay. And so here I'm using now f because we want to think about functions intuitively, okay? And what is the inverse problem? Well, you have some data y that comes from g of f0 plus noise, and you want to know f0. Very simple, right? Okay, and it also gives you a log likelihood function, this function g, right? that is essentially, I mean, if this noise is Gaussian, then you kind of have a least squares method, what Gauss invented more than 200 years ago. Okay, so the measure of how well a given f matches your data y is essentially this squared norm. Okay? Okay, but why can this be complicated, right? So obviously all the complication is in G. So I want to give you one example for heat flow, okay, where essentially this G map is the solution map of a PDE. And why would this be interesting? Well, because essentially the solution U is kind of, let's say, your temperature measurements in the room, while this thing here on the left is the heat conductivity that, you know, like maybe you're not in a room like this where it's just filled with air, but you have some material, and the material is inhomogeneous, and it has a different heat conductivity at each point, right? So this comes up in a lot of different settings, like in geology, for instance, underground, or in many other kind of diffusive phenomena. So here you have this kind of spatially varying heat conductivity, which you would want to know. And here on the right-hand side are the temperature measurements that are actually realized. This is the thing that is accessible to you, right? Okay, so how would you say this mathematically? Essentially, you're saying that f is a kind of this coefficient function here in a differential operator, which is divergence of f times gradient u, and there is a u that solves this uniquely, right? Okay, so this is just one example of a model that people have studied a lot, and this is a nonlinear operator, right? And so it's not so clear how to reconstruct f from just observing this, right? But you can use Bayes formula, right? So you can say, okay, for each f I solve my equation and I do my least squares functional. I put some prior on f, I weight that. Of course, everything has to happen in this kind of space of possible functions of heat conductivities, but miraculously it actually really works. Okay? Okay. Another example is a related equation which comes from quantum mechanics, Schrödinger equation, right? Again, a steady state. So you see here, for those of you who have seen PDEs, there's no time derivative. And what is this G operator here? Here it maps from f being here this kind of Laplace u minus fu. So this is what people would call a potential term, right? And you observe u, which is in a way kind of the state of your electron. And if you want, f is kind of some force or potential that is exposed to maybe coming from a proton. Okay? But this also turns up in medical imaging modalities. Okay? So these are just two examples of some kind of PDE problem that is much easier than fluid dynamical problems like in weather. Okay? I want to now also show you some other setting in which PDEs are used, which is kind of learning this kind of PDE or differential equation to generate images. Okay, so as I mentioned, here you start from a simple probability distribution, and you essentially learn this transformation that just transforms your kind of white noise that doesn't look interesting, right, into a very structured image. And a lot of these methods, like neural ODEs or diffusion models, are also based on kind of having a differential equation in between here. And you're learning kind of the velocity. Okay? Now, I think two more examples. Here's, okay, SDEs, right? So, this is super related to the steady state heat equation I was telling you, right? But here, when we think about SDEs, we're rather thinking about the same phenomenon perhaps, but on a microscopic level, right? So we're thinking about kind of one particle rather than the kind of heat profile, which is kind of an average of many particles, right? We're thinking about one particle that's kind of jiggling around, and in places where the heat conductivity is high, it's jiggling more, right? And here it's jiggling less. Okay? So this is also, you know, in molecular dynamics, for instance, I jiggle less perhaps when I'm in a very stable point, right? Like my molecule is in a certain position, and then I have certain unstable points, and I like to go to that other place, right? So there's a kind of spatially varying jiggliness, okay? And here's what the path of such a particle would look like. And what is a statistical problem that I could look at? I could say, well, we observe this kind of particle at different points in time. So let's say at some distance d, okay? And I want to learn this function f that is kind of describing my jiggliness from this data, okay? So here on the right-hand side, you would kind of see just low frequency states, right? So I can take an image of my particle every second, and I want to reconstruct this unknown thing here on the left, okay? So this is a problem. This is an example of doing statistical inference in SDEs, okay? And finally, this is maybe the most AI thing, or what people would intuitively think of when they think about AI in the sciences, is typically, if I have a model for my physics, I'm going to use a PDE solver to try to say, okay, given my heat conductivity profile, what is the corresponding solution, right? Typically, I would say, okay, I have a PDE. I know what the heat flow behaves like, and I'm gonna run an expensive, you know, like a numerical scheme in order to go from here to here. But now people have said, well, for one, it's super expensive every time to solve this PDE, and for a second thing, perhaps actually my model going from here to here is misspecified, right? Like I have some equation, but it might not be the correct one. It might be, you know, like imprecise. So what if I put a lot of input-output pairs, a lot of, you know, like a lot of example training data of possible heat profiles and heat equations and solutions, and I just put a neural network and I train it, right? And this is what people would call operator learning. I'm trying to learn the operator going from the left to the right. Okay? And this recently has generated a big hype. It works well in certain settings, but not always. And we're also trying to develop some statistical foundations for this kind of problems. Okay. So how much time do I have? 15 to 20 minutes? Okay. All right. Okay. So now I want to tell you about some results that we were able to achieve in these kind of problems. Okay. So statistical theory. Okay. So there's a lot of jargon, and I encourage you to think in the big picture, which I guess is my job to make you think in the big picture. But okay, so in this setting of inverse problems, right, where you have this transformation G between what I want to estimate and what I can observe, okay, a few years ago there was very little theory for the case where this G is nonlinear. But in practice, almost always this operator G is nonlinear, okay? So we were able to derive some mathematical kind of convergence theorem, okay? That is of the type, if I have n measurements, I will have estimated my object of interest up to some precision with high probability, okay? So what is the condition under which we are able to do this? We essentially need to bound the difference in two PDE solutions given two heat conductivities, okay? And now the math majors amongst you, or PhD students, researchers, we'll notice that here I put some norm, which is essentially in what size do I measure the difference, okay? And I have another norm, another measure of size on the right-hand side, and they're kind of different. And so this is the so-called L2 norm here. I have a so-called negative Sobolev norm, right? And essentially what this encapsulates is that this operator G might have smoothing properties, okay? So essentially I might say, well, these two things are in close in one measure of size, and here on the right hand side I have to put just I have to put a different measure of size, because this might behave like the derivative of this, or this might behave like the integral of this, right? So your okay, and so kappa is essentially the order of smoothing. Okay, so how much smoothing is going on when I go from f to g of f. And what is the theorem that we have? Okay, just look at the formula. You can forget about the text. I should have deleted that. Okay, so the theorem is an example of a bound for the so-called mean squared error. Okay, so what is the mean squared error? It's essentially saying if my data come from some f0, and my data are random, right? Because I have these random measurement noises. So I can never prevent myself from being off in some kind of outlier event. But on average, right? So this is why I have this expected value here. On average, I can bound my error, right? Okay. And so this is essentially bounding the error of the maximum a posteriori estimator in this nonlinear inverse problem. And its reconstruction error to the truth. And here we have some convergence rate that maybe very a few people of you might be familiar with, but the nice thing is this is an optimal rate. So you can prove that in a lot of problems there is no algorithm that can do better, okay? Which is a different like I'm not telling you how to prove this. It's you know, like there are techniques for that, but it's very nice and reassuring, right? In this case, we've shown that Bayesian methods based on this maximum a posteriori estimators are as good as any method. They're kind of extracting the optimal amount of information from the data. Okay, and for the people from the subject, so what we use is kind of ideas from M estimation. So M estimation is essentially estimators who are derived as maximizers or minimizers of something, right? And in this case, they're the maximizer of this posterior density. And there's a very well-established kind of machinery to analyzing these, but it has never been combined with PDE theory before. Okay. Okay. So here's a numerical simulation, actually, that illustrates a little bit this kind of convergence, this dry mathematical result I just showed you. So on the top, we see kind of a typical draw from the prior. So because people put prior distributions, right, on F. And this is a so-called Gaussian process prior, right? And so it will look very unstructured. It's kind of just what we believe could be a possible F a priori. And after observing the data, as we observe more and more data, we see that we are kind of reconstructing this ground truth with these 4 high diffusivity regions, right? And so essentially, yeah, this is the numerics for the theorem I was just showing you. And essentially, as n grows, you will get arbitrarily close to the true solution. Okay? So this is one type of thing that people in our field are trying to do. Now, I want to tell you next about another kind of flavor of mathematical result that we care about, which is in the previous result, I told you about this f hat. And this f hat was the maximizer of the posterior. But I have completely not told you about how to compute that, right? So it's like saying, oh, if I have a huge number, the prime factorization of the number will satisfy property x. But actually, as we well know, computing the prime factorization of a huge number is a very, very difficult problem, and it might actually be take you an impossible amount of time, right? I mean, our encryption systems are based on that. And in statistical problems, this can happen too, that you have a method that looks super nice and you can prove this nice property, but it's actually uncomputable. Okay? So how do you even generate samples from the posterior distribution? The most common way is a method called Markov chain Monte Carlo. Okay? So you, because actually this posterior distribution pi of theta given Zn is very complicated. It's not like a uniform or a Gaussian distribution, which you might have learned, you know, how to, or you might have even implemented in the computer, how to generate a sample using a random number generator. This is much more complicated, and it's actually very difficult to generate a sample from that, right? Especially given that theta is very high dimensional, okay? But what people do is they very clever people actually in the Los Alamos labs in the 1950s came up with this Monte Carlo method, okay? And okay, what's the general idea? You kind of design a dynamical system that kind of is evolving in time. So this is the theta k, where k is my time parameter. And I let it run for a very long time. And I know that if I let it run for a very long time, my dynamical system will converge to this posterior distribution by design. Because this posterior distribution is what's called the invariant distribution of this dynamical system. Okay? So this is a super clever idea. And one famous MCMC algorithm is the so-called Langevin algorithm, right? It's used all over the place, also in machine learning, where essentially what you're doing is your dynamical system is taking the previous step, theta k, and going to the next step. What do you need to do? You take some step in the direction of the gradient of the logarithm of the density that you need to target. Okay? So, okay, gamma is the step size, and you go kind of a step in the gradient. So those of you who know gradient descent, this is what you would do, right, in gradient descent. But then additionally, you're adding kind of a noise term. So you're saying I'm taking a gradient, and I'm actually taking a stochastic gradient. And many of you know stochastic gradient descent, right? This is what you would do in stochastic gradient descent. Except in stochastic gradient descent, you would make the noise maybe not of this order square root gamma, but of a smaller order, right? Because if I think of gamma very small, then the square root is much bigger than gamma itself. So here I will actually have much more noise than I will have gradient. Okay, and this is why I'm not gonna converge to some point, but I'm gonna converge to the distribution, right? And one can show that this has the right invariant distribution. So essentially what I need is I need to be able to calculate my gradients, and then I already have an algorithm to generate my samples. That's pretty nice, right? Okay, just to give you an example of an MCMC algorithm. So here, I need to share the screen. I have a little video. Okay, so I have a two-dimensional distribution. So here you see so here you see it kind of has three high probability regions. Okay, and here we see the distribution of the kind of projection onto the left and the projection onto the bottom. And the Markov chain is kind of walking around, right? And we know it's going to have the right invariant distribution eventually, but right now we see it's actually spending a lot of time here because it kind of is only locally moving, right? If you always follow the gradient, you're kind of going to stay there. But at some point, the noise is going to be so big, you're going to jump over. So, okay, so here we see it has not yet converged to the right distribution, right? But we know by design it will eventually. So the question is, how long will it take, right? Yeah, I didn't show you a video where it actually works. So here it hasn't worked, right? And that's the problem, right? I might, in my ML system, I don't have a 2-dimensional system, but I have a 10,000 dimensional system, and I just run my Langevin algorithm, and after 1 million time steps, I tell my boss, like, look, I've generated these samples, but you actually, you can't be sure that you've generated the right samples, right? Okay, so that's why we have thought quite a bit about these kind of problems. And just to show you, okay, so the question is, what is the computational complexity in mathematical terms of sampling from some high dimensional posterior? Okay, and okay, there's some previous work on this by famous people. For instance, some of you might know Martin Heira, who won the Fields Medal for his work on stochastic PDEs. But Duke just told me I have 5 minutes, so I shouldn't get lost in these details. Okay, so I want to tell you one theorem we proved, and I invite you to ignore all the upper part. Okay, so the gist of the theorem is the following: that in some of these models, and you really have to go model by model, like for instance the Schrödinger model. By now it's also been verified for this for this heat equation model, and it's being also worked on for Navier-Stokes systems and things like this. We proved that these MCMC algorithms are essentially polynomial time. Okay, so polynomial time, you go to some practitioner, they will ask you, okay, so but what polynomial, like n to the power 100 or what? Like because if you have n to the power 100, that doesn't mean it's feasible, right? But this is a theoretical approximation of the term that something is computationally feasible, right? So we showed that essentially you can compute the posterior mean and also the MAP estimator in polynomial time. Okay, so this is an interesting insight. And it's not clear whether it's possible in general, right? But for these models, we now know that. Okay, and it's proof's complicated. You can ask me about it after over a drink. It's essentially related to log concave approximation of posterior distributions. Okay, but then we also noticed that actually one can design situations in which MCMC fails, and it provably fails. And this is this notion of algorithmic hardness. So here's another result. We showed that essentially there are operators G that are very mean to you. And they're mean in the following way, that actually, the posterior distribution, it does concentrate in the right region, right? So what does this posterior contraction mean? It means that most of the posterior, like the orange bars that I showed you, will be around the correct solution. That's number one. But then when I tried to sample from it, I have this thing that's called exponential hitting time. And I should also mention the middle property, so unimodality, which means that the posterior actually looks kind of harmless. Because not only does my posterior concentrate around the right answer is also where the posterior probability has the highest density, right? So there are no other kind of local minima, like I showed you, that are really, like that might deceive you. And yet you have this kind of exponential hitting time, which means if you don't yet initialize close to the correct answer, any local algorithm, so any Markov chain that kind of makes small steps and tries to explore space, will take an exponential time to find the right region where the correct answer is. And this has to do essentially with the fact that these models can be very high dimensional, and in high dimensional space, if you think about it, right, the higher my dimension, the quicker volume grows when I go out, right? So essentially then the algorithm gets lost in exploring outer regions because they have a lot of volume compared to a little region where your true answer lies, okay? And these are ideas that kind of come from statistical physics, actually. So this is, these algorithmic hardness questions in general are very interesting to me, and they kind of bring in new ideas from kind of computational theory. But I think I'm almost at the end of my time, so I'm just going to very quickly sketch out this kind of neural network surrogate ideas. Okay, so this is, you know, if you want, the closest thing to my talk title of actually learning the physics, where you're trying to kind of in a black box fashion say, I'm going to learn the parameter to solution map of my PDE. Okay, and the way people do this is, of course, you know, in a computer there's nothing really infinite dimensional. Right? These, you might think, oh, function space is infinite dimensional, but in a computer you always discretize things, right? And what people do is they discretize this function to a finite dimensional thing, but very many finite dimensions, right? And my output space also very many finite dimensions, and in the end you're putting a neural network between two Euclidean spaces that are very high dimensional. Okay, and you train the neural network based on these input-output pairs. Okay, so the question is, can you learn some G hat? Okay, and as statisticians, we think of, this is regression, right? So this is regression, but between infinite dimensional spaces, between Hilbert spaces. And yeah, these methods work very well. So there's Fourier neural operators and deep O-net papers which came out less than 5 years ago, which now have like, I don't know if it's just thousands or tens of thousands of citations. Okay, and essentially one thing we have been doing is we've been trying to develop the statistical foundations of this. And actually we just recently got the first result that is again kind of polynomial time in the samples. So what did we do for this? Okay, Darcy flow is essentially this heat equation problem. So again, ignore most of the text because I'm going much too fast. Okay, just essentially look at this convergence rate. It's now for the mean, it's again a mean squared error, right? But what it is saying is actually I can learn not just one F0, like before I was interested in reconstructing one heat source, but actually I can learn this whole complicated mapping from all the possible heat conductivities to all the possible temperatures, right? That is a mapping that's much more complicated because it goes between infinite dimensional spaces. And if I give my neural network n training data, and what is training data in this setting? It's kind of pairs of this input and so the heat conductivities and the solution. If I give my operator n pairs, I'll get a mean squared error that is of the order n to the minus some power rho, right? And so this is, in particular, this is a polynomial convergence. And in statistics, in general, when we're trying to do something between infinite dimensional spaces, there's this thing called the curse of dimensionality, right? So we do not expect that for infinite dimensional spaces, you know, there should be something possible that is polynomial, right? So a priori, you can maybe expect something like 1 over log n, right? Which is much, much slower, right? So you give a million samples and 1 over log n will be equal to 6 if you take the logarithm with base 10, right? Whereas this will be much faster for even any polynomial rate, right? So this is something we've been developing. And okay, there's a general theorem underlying this and some nice proof ideas. We also try to develop new algorithms, for instance, in the context of diffusion data. But in general, I just want to say that there's a lot of, I hope I've given you a sense of the things that the community thinks about. And there's a lot of open questions, both of mathematical nature and of more philosophical and kind of meta level nature. And you see the field is messy. There's a lot going on. There's a lot of different settings where these tools come together. And if you're interested in learning more, I'm happy to chat.
Okay, with this we want to open the floor to you guys. We're going to do a quick Q&A, 10 minutes. So just please raise your hand and we're going to have Anna bring you the microphone so you can ask the question.
if you go back to the heat equation with the neural network in the middle. Yes. I mean, in this case, the neural network is always predicting the next step in like some finite time quanta, right? Because normally, like from what I remember, like you can, with a PDE, you can do like step by step, and then the step is like variable by which you want to do it with the PDE. But if you stick it in the neural network, can you also like change the duration, like for example, the time in the heat equation, if without retraining the neural network?
Okay, so I should clarify, this is actually the steady state formulation of the heat equation. So in some sense, here I'm just learning the mapping that maps my heat conductivity, not to successive heat profiles, but kind of the equilibrium heat profile. Okay, so there's no time involved in that sense here. So in some sense, it's a purely static problem. But in general, I think people have been on a meta level, right? Thinking about neural networks as methods that are kind of, that can get rid of these discretization choices that you need to make, right? So for instance, if you traditionally want to solve this, you need to define kind of a mesh on which these PDE solutions are defined. You know, similarly, like you need to give time discretization. But now here, kind of with your neural network surrogate, you can evaluate it on any kind of input that doesn't need to necessarily be on a mesh, and your training data doesn't also need to come everything on the same mesh. So in general, yes, you can get a little bit rid of these usual numerical maybe choices that are a bit arbitrary using.
So I come from the background of the humanities, specifically statistics. Sorry, not statistics, obviously, linguistics. And obviously we use R and specifically STAN for Bayesian statistics, which is supposed to be this super efficient implementation of MCMC. So I was wondering, because it doesn't look like you use R, what is the toolkit that you use?
So for our simulations, because of all the PDE stuff, we use MATLAB or Python, which I think in R maybe is also possible. In STAN, for instance, you have MCMC implementations that are very optimized and that make a lot of choices for you, right? So for instance, there are algorithms that are like Hamiltonian Monte Carlo or this no U-turn samplers, and things like, you know, this gamma, which was the step size. You need to tune all these. You need to make a choice of that in practice, right? And STAN does a lot of that for you. And yet, and I agree that it's very efficient, and yet often you don't have these kind of convergence guarantees, right? So you have a toolbox that essentially is made for, you can throw it at any problem, as long as you have some kind of posterior density that you can evaluate. But yeah, so the theory depends on the concrete model you're looking at. Yeah.
Thank you very much for the nice talk. It was very great. I have two questions. I hope that's okay. The first one is about your last theorem. You had this polynomial convergence rate with some rho. And I don't know if I missed it. Is this rho, is this also an optimal rate? Because you talked about optimal rates earlier. Or how does it depend on the dimension and the smoothness of your operator?
Sure. And what's the second question?
And the second question was about your negative result, where you said that the MCMC didn't work for a constant step size. Yeah, is there a similar result for a variable step size?
Aha, okay. Yeah, these are both very, very good questions. And obviously, yeah, you work in this field, so. So with regards to rho, rho is essentially rho is essentially kappa divided by kappa plus 1, where kappa is the rate at which you can approximate these operators G. Okay, so previously it was already known that if you take a neural network of some certain size, right? How well you can approximate these solution operators. And now if you take that approximation rate, you get this, and the novel theory that we developed, you get this kind of statistical rate. The thing is that this theorem is very recent. It's from maybe 3-4 weeks ago. And there was no such convergence rate at all before that. So we all have no idea about optimality. And this is something that we're going to work on and hopefully figure out in the next months. It always takes longer than you think. But yeah, so we don't know what the optimal rate there is. In these other problems, which are much more traditional, like in the inverse problem, the optimal rates are well known. And here, nobody has been able to prove kind of lower bounds yet. Yeah.
Thanks for the talk. Would I be right in taking away a broad understanding that for these inverse problems, they're somehow very favorable to parallelization? I'm thinking about these results with neural networks, like in contrast to, say, if you asked a neural network to predict which stuffing well you would end up in after time t, or predicts the location when you have some positive Lyapunov exponent, right? This would be like an exponential sequential computation. But yeah, is there some kind of link between these inverse problems and parallelizability?
So I have to. This is a very, very good question, and I think many clever people, especially from actual, computer science, who are implementing these things, think a lot about, training these things, right? And often you want to parallelize your, let's say, gradient descent algorithms. And of course, neural network gradient descent algorithms are very optimized. You subsample. I'm not sure if inverse problems are actually inherently good for parallelization, right? So one way you can think about parallelization is, or distributed computing, right? Is you have a ton of data, and you have several processors that are, all available, but you kind of want to feed smaller data sets into each of these. And then you kind of want to maybe locally learn some estimator, and I'm making a gross oversimplification, right? And then you have estimators that are, or best guesses that come from each of the small data sets, and in the end you aggregate them again, right? And there has actually been some really interesting statistical foundational work on distributed inference for non-inverse problems when you don't have G involved, right? But actually, at least from a statistical theory point of view, we don't yet know this kind of result where you can do distributed computing. I've discussed it with several researchers in this area, and it would be really interesting. I'm not sure, just from purely algorithmic point of view, if you wanna minimize, this kind of objective function, what the best thing is to do in terms of parallelization. But I know that it's an important question.
So this might be something that you think about a lot. Again, in my field, it's a bit different from physics, I imagine, because we have typically very, very low sample sizes. It could be that we only have 60 participants in a study, 60, 70, something like that. And then what we often do is we do a meta-analysis to choose a prior. And other than that, we can basically just look at our data and decide on a prior because of that. And my lecturer says, okay, basically you develop a feeling for how to choose a prior, and obviously you still do sensitivity analysis, but yeah. So my question is, how do you choose a prior for your models?
Excellent question. And this is a very, very deep question, I would say, about the kind of philosophical aspect of statistical inference, right? So one thing that's for sure is that a priori, you have to kind of make up your mind what information you're allowed to use when you're picking a prior, right? So for instance, are you allowed to pick your prior after observing your data, depending on the data, right? And maybe to a certain degree you are allowed to do that, right? Maybe I'm allowed to say, well, I'm not picking the whole prior based on that, but I just have, I have already a pre-selected family of priors, and I'm just picking from these 5, right? So that you could do, and that has a name, and people are studying that since decades, actually, and it's called empirical Bayes. So empirical Bayes is almost like internally contradictory, right? But you're saying I observe my data, and then I pick my prior based on that, and you then do inference based on the posterior that comes from that prior. So this is a bit circular, but in some situations you can do that, but you have to be careful, right? And in terms of here, how we pick our prior, it's true that the prior, all our results rely on the prior being kind of correctly chosen. And what do I mean? For instance, this optimality result for the convergence of the posterior, right? And the correctness is essentially saying that my prior needs to resemble F0, my true solution, well enough. So for instance, if F0 is a function that, doesn't have crazy jumps or has varies on a certain length scale or has a certain smoothness, my prior needs to kind of also resemble that kind of regularity, right? And in that sense, I think your lecturer is saying the correct thing, right? If you believe your parameter should be somewhat in this kind of region or should satisfy certain properties, your prior should reflect that, right? And recently, there's actually a really exciting work of purely data-driven priors, actually, for instance, in medical imaging, right? So if you think about MRI images, right, and let's say you have 100,000 brain scans from people, the prior you pick should somehow be like, okay, a distribution that only gives you kind of plausible images of a brain. And we haven't been able to actually mathematically encapsulate that, using, let's say, I don't know, the space of 3 times differentiable functions. So what people in ML have been doing is actually learning this kind of prior. And then when you have measurements from a new patient, you use this like learned data-driven prior. And this gives really, really good results. And this is again something where we don't yet have a lot of theory. But yeah.
Method.
What is the Newton method?
The Newton method. I mean, if you start from a good point, you may converge. If you start from somewhere randomly, then you see my point, So those kinds of behaviors are not very surprising because in the nature of research they've seen.
Sure. So a priori, you don't have any reason to believe in the global convergence of the Newton method, right? But there are conditions such as convexity that actually give you convergence. The problem is actually, for the experts in the room, the main problem is that all these computational problems that we have here are usually non-convex, right? So when things are convex, you can optimize the function. When things are non-convex, which is always the case actually for neural networks, it becomes very, very complicated to give any guarantee on what the algorithm is outputting. And this is why we're studying these questions. And yeah.